Well, the moment has arrived at last. We've come to session 14, our final session. This too is an advanced topic session, and if you've persisted all this way, I give you a metaphorical pat on the back. Really good job coming this far. You've learned a lot of things, you've written a lot of programs, and we're going to cover just one more thing, and then we will say goodbye and leave you to use your newfound knowledge of IPOS to develop absolutely incredible applications. So what are we going to do in session 14? We're going to learn about Fieldbus communications and writing IPOS programs to make them possible. SEW Eurodrive is very good with Fieldbus support. We support almost every major Fieldbus standard on the MoviDrive B. Let me give you an example of some of the Fieldbuses we support. First of all, we handle all what I call the classic Fieldbuses. These are the ones developed in the 80s that have been around forever and that people have been using and using and using. By today's standards, they're getting a little bit long in the tooth, but they're still useful and you still encounter them all the time. Now, these are the cards available for the MoviDrive B to support classic Fieldbuses. We support CANopen, DeviceNet, Interbus fiber optic, and Profibus. Put one of these cards in a MoviDrive B and you can communicate with some of your classic Fieldbuses. But of course, SEW doesn't stand still, and we support the modern Fieldbuses as well, which tend to be based on Ethernet. And these are the Ethernet-based Fieldbus cards that we support. We have one for Profinet, one that supports both Ethernet IP and Modbus TCP, and one that supports EtherCAT, the real-time version of Ethernet Fieldbusing. So these are available as well. Finally, we have a number of discontinued Fieldbus cards that I'm just going to mention since you may encounter them in legacy applications. We have an earlier Profinet version, an earlier Ethernet IP version, and an earlier Modbus TCP version. How do you tell these apart aside from the part number? Well, it's easy. The current Fieldbus cards that use Ethernet have two ports on the front. They contain a little mini hub to make it easy to chain devices together. The earlier ones have just a single port, and so if you needed to chain them with something else, you had to use an external hub. That's how you tell them apart. But functionally, they do the same thing, so it really doesn't matter what you're using. If you've got one, you can get on a Fieldbus and start communicating. Now, with the Ethernet Fieldbus cards, you need to know a few things about how they're configured, since these are the ones you're most likely to encounter. All SEW Eurodrive Fieldbus cards based on Ethernet have a default IP address of 192.168.10.4. This can be changed, of course, but if it's brand new out of the box, that's its IP address. And you can use that when you're developing programs to communicate. Now, all these cards have two little dip switches on them, and one of them can be used to force the IP address back to this default value if somebody has changed it. So you can use this switch to put it back to a known condition. Here's how you do it. You set the switch to 1, and you turn on the MoviDrive B, and then you turn off the MoviDrive B, and you turn the switch back to 0, and then you turn back on the MoviDrive B, and the card will now be back on the IP address 192.168.10.4. Really handy to know. You may be wondering, what's that AS dip switch? Just leave it set to 0. The only time you would change it to 1 is if you're using this Fieldbus card in the UOH21B gateway. That's an external enclosure. You can put the Fieldbus card in there and use it as a kind of gateway. That's really a specialized application. You may never actually see that configuration, but that's what the switch is for. So let's talk about Fieldbus control if you're new to the topic. All the major control companies use Fieldbuses. The PLC manufacturers do. Fieldbuses are really where it's at. And a lot of SEW Eurodrive's newer products, the Movi C generation, are heavily Fieldbus based. So let's talk about Fieldbuses a little bit. This is a typical Fieldbus setup. You have a group of VFDs with Fieldbus cards in them, and you have some kind of a PLC, either one of the SEW controller type PLCs, or one from a manufacturer like Allen Bradley or Siemens or Beckhoff. It doesn't really matter, but that PLC will have a Fieldbus adapter in it, and the Fieldbus will just join everything together. It will connect the PLC to all the VFDs, and the PLC can then send commands to the VFDs to make them do interesting things, and the VFDs can report their status back to the PLC. And of course, since you've learned IPOS, this gets much more powerful since you can have IPOS programs running in the VFDs doing very sophisticated communication and control tasks and then passing information back to the PLC. Now, devices on a Fieldbus communicate with each other by exchanging what are called process data words, sometimes abbreviated PDs. Process data words go back and forth across the Fieldbus. And it's important to understand that everything is viewed from the perspective of the PLC. The PLC is communicating outwards and receiving information back inwards. So we call process output words, POs, as words that go from the PLC to the VFDs. These typically send commands and parameters to the VFD to control what they do. Process input words, or PIs, go to the PLC from the VFDs. Usually PIs carry status information that the PLC wants to know. Kind of like this. POs go out from the PLC to the VFDs, and PIs come back. And you notice in each case here we had 3 POs or PIs. That's a very common communication standard where we send 3 process data words in each direction. All right, let's talk about process data words, what they're like, how they work. First of all, process data words are 16-bit binary numbers. We've been working with 32-bit binary numbers a lot in the last sessions as we learned about things in IPOS, because IPOS works with 32-bit numbers primarily. But PDs are actually smaller. They're 16-bit binary numbers. This is a typical process data word. And again, its bits are numbered just like IPOS variables were, starting at bit 0 and going up to a maximum. In this case, only 15 instead of 31. Process data word can perform 2 different types of functions. Either the bits within the word are individually significant. In other words, they're like switches or control bits, where individual bits turn things on or off, or they report information by on-off status. That's one way that process data words can function. The other is that all the bits together just form one big binary number, and that binary number means something. Maybe it's a parameter, a setting, a status word. Who knows? Doesn't matter. It's a number. So let's look at examples of each. Let's look at the first type where the individual bits behave sort of like switches. We'll look at a process output word first. The individual bits in this would perform individual control operations. For example, you may have a bit to cause a controller inhibit and enable, select direction clockwise or counterclockwise, maybe do an emergency stop. These would be individual bits that you turn on or off to make things happen, the red bits here. The black bits are what we call don't cares. They don't do anything. They're just there to fill up the word, but if you flip them, they don't really perform any function. By the way, I should mention that the example I'm showing you here is a generic example. It has no connection to any SEW product. I just made it up as a simple illustration. So don't expect this to work anywhere in an SEW product. Let's look at a process input word. Process input words that use individual bits probably are providing status information of different kinds. For example, it indicates if something's ready, if a brake is engaged, something's stopped, or a fault. Again, individual bits where on or off simply means yes or no. And again, we have a lot of don't care bits that don't mean anything. So that's process data words of the first type. What about the second type? Well, with a PO, a process output word, maybe the bits form a binary number that's a control parameter. For example, Maybe we're setting a speed of a VFD, so we send a binary number signifying speed. For example, these bits together combine to form the number 1000, so maybe that's setting the speed to 1000 RPM. And if we send that process output word from the PLC to a VFD, that might make it spin at 1000 RPM. Pretty simple. With process input words, often we have numeric status information. For example, maybe we have a process input word going back to the PLC telling us what our current position is. The VFD is reporting where the encoder is reporting the drive is positioned. So maybe it sends back this, which happens to translate to minus 20,806 millimeters. So a number. I should probably heads up you on the fact that a 16-bit number has a numeric range of basically plus or minus 32,000. Actually, it's minus 32,768 to positive 32,767, assuming it's a signed number. If it's an unsigned number, then it's going to go from 0 to something twice as big, 65,535. Just depends on the application how the number's interpreted. Could be signed or unsigned. But that's the numeric range. Now, that's a big range, but in positioning applications, it really isn't. 32,000 millimeters is not that much. It's only 32 meters. And on a big assembly line, you could definitely have something longer than that. So what do you do if you need bigger numbers? Well, it's easy. You chain two process words together, two POs, two PIs, and you can create bigger numbers. Let's look at probably the simplest form of Fieldbus control. It's called 1 PD control. And we call it that, as I'm sure you can guess, because the PLC and the VFD exchange 1 PD in each direction. Kind of like this. A PO goes out, maybe with control information, and a PI comes back with status information. So it's a very minimal communication scheme. It's one of the simplest forms of Fieldbus control. In fact, it's a lot like binary control or terminal control mode, where you're doing just this very simplified control, but you're using a Fieldbus instead of a lot of digital I/O lines, so it is more efficient. Several SEW products do support a 1 PD control mode. Let me just summarize it very quickly. The PO is used for control, and it has these bit positions. Bit 0 is a software controller inhibit. Bits 1 and 2 are enables, and they can provoke two kinds of stops, a normal stop or a rapid stop. Bit 6 is used for resetting faults. Bits 9 through 11 can select from 6 different speed set points. Bit 12 selects direction, either normal or reverse direction. And bits 14 and 15 select from 4 different ramps. So a number of SEW products do use this communication scheme. It's really just fancy binary mode. Now the PI word that comes back is a status word, as you can guess. And here's what the bits mean. They indicate if the motor's turning or not, if the inverter's ready, if the drive is referenced, if the set point has been reached, if the brake is released, if there's a warning of some kind, if there's an error on the VFD. So by passing these two words back and forth, the PLC and the VFD do a kind of binary control, but over a Fieldbus. Now, as you can guess, this is a little bit limited what you can do with it. What if you want to do something more sophisticated? Well, you use 3PD mode. 3PD mode, as you can probably guess, involves 3 process data words being exchanged in each direction, and that is much more powerful. So maybe something like this. The first process output word contains control bits, the second contains a speed value, and the third contains a ramp value. And then the VFD passes 3 words back to the PLC, providing status and information about how much current the motor is pulling. So this is much more sophisticated. You can do really good stuff with 3PD. Many SEW products use this mode. And there are other control modes. For example, some products use 5 process data words, or even more. It just depends what the application is. But 1PD and 3PD are very, very common. So if we're going to program Fieldbus communications in IPOS, what do we have to do? Well, surprisingly little. It's actually pretty simple to set up Fieldbus communications. We do need to do one thing. We need to go into the parameter tree, and we need to go to parameters 870 through 876 and set those up so that they are set to IPOS PO data and PI data. That's essentially saying that IPOS gets to read and write the process output words and the process input words. So you need to make these parameter tree changes. And of course, if you have an Ethernet Fieldbus card, then you have to go in and set its IP address perhaps. If you're using a classic Fieldbus card, usually addressing is set with dip switches. Once you've done all this, it's now entirely up to your program to deal with process output and process input data. You read the POs coming from the Fieldbus and you write PIs back onto the Fieldbus. And really, that is it. So how do we transmit and receive these process data words? Well, guess what? There's a function in IPOS called getSys. You've actually been exposed to getSys already. We talked about it a while back. We did some different things with it. But amongst its many capabilities is the ability to communicate over a Fieldbus card. Now, as you can see, it's using some of those built-in complex data types. You give it a variable of complex data type GSPOData3. So you have to create a record variable, and that's why I taught you about record variables in our last session. You create a record variable, and you pass it to getSys, and then you give it the constant GSPOData, and that will retrieve Fieldbus information, actually POs, into a record variable. And then you can pull those out, and you've got your POs from your PLC. And to communicate the other way, you use our old friend setSys. And what you do is you pass it the constant SSPI data, which tells it you're doing PI communication. And you create, again, a record variable with a built-in complex data type called SSPI data3. You pass it in, and you make sure that you've created your PIs and put them into the right variables within that record variable. And that will then automatically, when the function is called, transmit the PIs to the Fieldbus. It's actually really simple. Now, what most programmers do, they don't do this in task 1, which is kind of considered a foreground task. They start up one of the multitasking background tasks, either task 2 or 3, and they let it automatically send and receive process data words. So it's kind of taken care of in the background, and I will show you how to do this. Meanwhile, though, let's take a look at those complex data types that we have to use with those functions. All right, this is our first one, and I've just called this one Fieldbus PO var1. This one is used for getting the POs that are coming from the PLC. So here are the variables inside the record. The first is called bus type, and you set it to 3, which means Fieldbus communication. You then have to set a length variable, and you set it to 3, and what that means is do 3 PD communications. And then the remaining 3 variables are the POs, PO1, PO2, PO3. So the information from the Fieldbus that the PLC has sent will be contained in here. So you extract these 3 variables, and those are your 3 POs. The second type is used to create a record variable, which I've called here Fieldbus PI var1, and this is used for sending PIs. Again, you have to specify the length. You set this to 3 for 3PD, and then it contains the 3 PIs. So what you do is you just put the information that you want to send back to the PLC in there, call the function, and they'll go zinging over the Fieldbus back to the PLC. Really, really simple. All right, now let's talk about a tool that SCW offers, and you can download this from our website. In fact, I've included a link in the description where you can get a copy of this. It's a program called the Ethernet Master Simulator, and it is used to simulate a PLC talking to a VFD. It runs on a PC. It's a Windows application. So you can just put it on your PC, connect your PC up to the Fieldbus card on a Movi Drive B, and you can pretend your PC is actually a PLC. And you can send process data words to the VFD, and you can receive them back. So it's a very handy development tool. If you're not super up to speed in PLCs, you can use this to develop code, and then you can hand it off when it's working, and that person can create the PLC code. So let me just give you a quick overview of the program. This is what it looks like. It's a very simple program. Key features. As I said, it simulates a PLC talking to a Fieldbus connected device. It's used for testing and diagnostics. It works with both Ethernet IP and Modbus TCP devices. It does not work with Profinet. If you want to deal with Profinet, you'll have to go somewhere else for a simulator because we don't offer one. But you can certainly buy one from someone else and communicate with our Profinet cards. And it just sends POs to the device, and it monitors the PIs coming back. Really simple stuff. I will mention, usually you need to register this program with your firewall, the Windows firewall or some third-party firewall if you have one, because since it's dealing with communications over a network, usually a firewall can block it if you don't register the program. And I will show you how to register it with the Windows firewall if that is what you have. One thing you generally want to do when you're communicating with the Ethernet Master Simulator is set your PC's Ethernet port to a fixed IP address. Fixed IP addresses are much easier to use when you're doing development. So what you do here is you would locate and open your network adapter, and I'm being a little generic here because everybody's computer is a little different, and different versions of Windows vary a little bit. But you find your Ethernet adapter in the control panel or its equivalent in your system. You change the IP4 settings to fixed values instead of using DHCP, which automatically acquires an address. So you go in, you pick Internet Protocol version 4, you select its properties, and then you change from obtaining the IP address automatically to using a static IP address. Then you put in the IP address, the subnet mask, and the default gateway. And in this case, if you're talking to an SEW card that's on a default address, which remember is 192.168.10.4, the address I have here, 192.168.10.100, is perfect. That'll be in the same subnet, and that will work fine. You set that up, you set the mask, you set the gateway, you click OK. Now, the Windows firewall. This varies a bit depending on your version of Windows, so yours may be slightly different, but here's kind of the big picture. Open firewall and network protection. You can use the Windows search tool, that's the magnifying glass tool, to find it. Pick allow an app through the firewall. Then what you do is add an app to the whitelist here so that it will be permitted to communicate. You pick change settings. You click add another app. Then you browse to wherever the Ethernet Master Simulator is located on your hard drive. Then click add. And then last thing to do, confirm that the checkboxes for domain and public are both checked. Click OK, and you're good. And at that point, you should be able to fire up the Ethernet Master Simulator and communicate without being blocked. So you fire up the program. Enter the IP address of the unit you wish to control. This is the VFD, and again, notice we're using the default SEW address here. Of course, if yours is different, obviously use that. Pick the protocol, either Ethernet IP or Modbus TCP. Set RPI to 500 milliseconds. Click Open Session. It will change, and then click the Start button to start communications. And you should see something like this. Notice it can communicate with up to 10 processed data words in each direction. Now, one thing you definitely want to do is uncheck Auto Update. If you don't do this, the minute you type in a value in one of the output columns, it will send it immediately. It is usually better to type everything in and then instead click the Update PO button and transmit them all at once. I find that works a lot better for development. So uncheck Auto Update and type in your POs and click Update PO to transmit them. Of course, PIs update automatically as they flow back from the VFD. So those are the tools that we are giving you to help you develop Fieldbus applications. And therefore, it is now time for a hands-on task. We're going to create a brand new file called Fieldbus 1PD. So you can kind of guess we're going to do a 1PD application. Okay, well, I'm going to give you a warning that you saw back in the senior project. Same thing applies here. We're going to be developing another program, and I just want to warn you again, this program is for educational use only. It is by no means a complete Fieldbus control program. It doesn't have all the features and safety capabilities that a full application would have. So I want you to be aware of that. If you use any of this code in your own applications, it's your responsibility to make it fully safe. It demonstrates the concepts that I want to show you, and that is really all. So remember, SEW Eurodrive does not accept any responsibility for injury or damages. That is on your head to develop safe applications. That said, let's talk about the program we're going to code, and it's a 1PD Fieldbus program. What we're going to do is develop a simplified 1PD Fieldbus control program that controls the drive using a subset of the SEW 1PD protocol. I showed you that a few minutes ago. We're not going to implement the full thing. That would be a much more sophisticated program than we could fit in one session that we're trying to keep under an hour. So we're going to do a subset of it, but it will illustrate the big ideas of Fieldbus communication. So here's how it works. Of course, we're going to be exchanging one process data word in each direction. This is the process output word that the PLC transmits to the Movi Drive B, and here are the bits that we're going to care about. First of all, the first 3 bits are going to implement whether the drive is running or in a stopped condition. Now, the bit pattern that lets it run is 110. So if that bit pattern is received by the Movi Drive B, then it should start the drive. Anything else, it should do a rapid stop, or if it's already stopped, just do nothing. In the complete SEW1PD protocol, there are actually 3 stops possible with these bits. There's a rapid stop, a normal stop, and a controller inhibit stop. We're not going to implement those. We're just going to have the run state and the everything else state, and we're going to use rapid stop for them all. So that is one simplification we've done here. Secondly, we're going to have our set point select bits. So these 3 bits determine which fixed set point to operate at. So these bits give us 8 different set points, 0 through 7. And I'm going to tell you what speeds to operate at, but these are going to control it. This is somewhat different from the SEW1PD protocol, which does not implement 8 set points. It implements 6. We'll do all 8. And then finally, we have a direction bit. If this bit is 0, the drive turns clockwise, and if it's 1, it turns counterclockwise. And that is it. There are going to be no other control bits here. Everything else is a don't care. Now, what does the VFD send back to the PLC in PI1? Just one single bit. So this is really stripped down. It is this bit right here. If the bottom bit, the least significant bit, is 0, means the drive is stopped, and if it's a 1, it means it's running. And that is it. So yes, it's really cut down, but this is going to be something we can code fairly easily. So that's our protocol. Now let's talk about our program and its general requirements. First of all, I'd like you to store the 8 speed set points as constants in the program, and I'd like them to have these values: 100, 250, 500, 750, 1000, 1250, 1500, and 1750 RPM. So just set those up as constants in the program. Yes, that's not as good because, of course, if you want to change them, you've got to change the code and recompile. But you've seen better ways to do this in other programs, and I want this program to focus on field buses, not best coding practices. I'd also like you to use a fixed ramp value of 1 second, both acceleration and deceleration, for all speeds. So we're going to simplify that as well. Field bus communication should be handled in the background by task 3. So you're going to use multitasking. The main task will handle the foreground activities, but task 3 will communicate on the field bus. It'll receive the POs and send back the PIs. We're going to use 2 digital signals on the option card. DO13 is a ready signal. That should turn on when the program is ready to operate. Remember, we usually do a 5-second wait to give everything time to stabilize, and then we turn on DO13 when we're ready. All the other digital outputs on the option card should be off. So this is the ready signal that would signal the PLC that it's okay to communicate. DI10 is an enable signal. Now this is going to determine whether the VFD listens to the Fieldbus or not. If it is on, then the VFD should listen to the Fieldbus and follow whatever commands come down it. If DI10 goes off, it should ignore all Fieldbus commands. So this is an enable-disable signal. This is often done on these kind of applications so you can sort of isolate the VFD from the Fieldbus just by turning a switch. So if the drive is running and DI10 goes off, stop listening to the Fieldbus, halt the drive, but do send a stop signal back to the PLC by PI1. In other words, turn that bit that signals stopped to signal that. So when it goes down and stops responding, it should send one final PI1. We're going to test this with the Ethernet Master Simulator, and the way you need to do it is put it in Modbus TCP mode. If you put it in Ethernet IP mode, you can have some problems. So Modbus TCP is fine. If you've got a Fieldbus card that supports both the Modbus TCP and Ethernet IP, you're good. All right, so those are the guidelines, and yes, it's fairly general. So I'm going to leave a choice here for you before I turn you loose on this. Either you can go off and try to code this using just what I've given you, and by now you should be up to that. Or if you feel it's a little over your head, then just wait, and I'll be stepping you through my code, and you can see how it worked. Okay? Your call. All right, before I turn you loose on the program, I want to give you a handy tip that might help you out a bit. IPOS does not have a built-in complex data type to support 1PD Fieldbus communications. It has one for 3PD and 10PD. So what does that mean? Are you stuck? Can you not do 1PD? Well, obviously there are a number of ways to approach it, but here's the easy one. Just use 3PD mode for this project and just ignore PO2, PI2, and PO3, PI3. You don't have to put anything in there or pay attention to anything that comes out of there. Just use the first process data word. And don't forget, set the length variable of the two record variables to 3. That will select 3PD mode and everything will work just great. So here we go. Pause the video and go do it. All right, well, let's go ahead and take a look at my code. And if you're just looking at the code, pay close attention, and I will step you through this in fairly good detail. But if you coded yourself, I'm hoping you had a splendid success, and you can compare your technique to mine, how you handled the Fieldbus. So here we go. Okay, well, let's take a look at my code. But before we do that, we need to make sure we've got everything squared away in the parameter tree. Remember, when you're going to control an IPOS program over the Fieldbus, you have to go to parameters 870 through 876 and make sure things are set up for IPOS. I have done that here. You can see I've set 870 through 872 to IPOS PO data and 873 to 875 to IPOS PI data. That means IPOS has full control of the Fieldbus. 876 is set to yes. So that means that we're ready to go there. I also need to check my Fieldbus card to make sure the IP address is okay. I do that by going to parameters 780 through 785, and as you can see, currently I've got my card set up to saved IP parameters. That's parameter 785. You change that from DHCP to saved IP. That gives you a static IP address. And then 780 through 782 should be set to the correct value. You notice I'm using the default SEW address of 192.168.10.4, which is perfectly fine for this application because I'm just going to be connecting straight from my PC to my Fieldbus card with a cable. Okay, so that is all I have to do at this stage. So now I'm ready to go to my IPOS code. As you can see, I've taken my skeleton program and I've fleshed it out. There's really not much I can scavenge from earlier programs other than just basic technique. So this is pretty much fresh code. So let's take a look at it and go through it step by step. First of all, in variables and constants, I have my set point speed constants. Remember, these were supposed to just be hard-coded into the program, and they are set point 0 through 7, and I have the values that I specified. Notice they have an extra 0 because remember, they're in tenths of an RPM, so we have that kind of pseudo-decimal place there. I then have a few constants to define I/O signals. For example, right here, I've defined ready as 3. That's the bit that will turn DO13 on and off on the option I/O card. I'm using this as a ready signal to let the PLC know that the VFD is ready to run or if it's still powering up. Following that, I have 3 constants associated with my operation. I've defined run as 6. That's the decimal equivalent of the binary value 110. Remember, if a 110 comes in on PO1, then the drive is free to run. I've also defined clockwise and counterclockwise as 0 and 1. That's the value that will be coming in on the direction bit. So I'm going to use these just to make my code a little more readable. Finally, I've created 2 constants to be used with PI1. That's the status value that goes back to the PLC. Remember, it has just one single bit that indicates the motor status. And I've defined stopped as 0 and running as 1. So that's what I'm sending back to my PLC. And that is it for constants. Nothing too complicated. Moving on to variables, I've created 2 record variables using built-in complex data types. I've used the complex data type GSPOData3, and I've called that variable Fieldbus1. That is the record variable that is used for information coming in from the PLC, in other words, PO1. I've created a second variable of data type SSPI data3 called Fieldbus2, and that is the variable for the outgoing Fieldbus word, in other words, PI1, that I'm sending back to the PLC. So I have to have these 2 records, and I'm going to use that with getSys and setSys to communicate over my Fieldbus. Then I've created just a couple general purpose variables here. I've created these called mode, set point, and direction. These variables will contain information that I extract from PO1 to tell me what mode I'm in, whether I should be running or stopped, which of my 8 set points to use, and which direction to turn. I'm going to be extracting this information from PO1 and putting it in these 3 variables. Finally, I have 4 variables here for setting the speed and ramp values. Remember, I always have to pass clockwise and counterclockwise speed and ramp up and ramp down times. So we're going to be using this with the setSys function to configure speed and ramp. And those, of course, have to be contiguous variables, so I'm putting them in order like this so that IPOS will assign them to contiguous H variables. That's it for variables. Let's move on to main. The first part of main gets the system initialized. So this is all initialization code. Let's step through that, and then we'll take a look at the background task where most of the key activities happen. The first thing we do is we do what we've been doing in most of our programs. We clear the option card outputs. We set them all to 0. We do a 5-second wait to give the system time to come up. And then we turn on the ready bit, which is DO13. That goes back to the PLC and tells it we're ready to roll. So that takes care of signaling the PLC. Then we go ahead and we set up our record variables. We'll set up Fieldbus1 first. That's the one associated with POs, in other words, what's coming into us from the PLC. I set bus type to 3. That means use Fieldbus mode. I set length to 3, which is going to select 3 PD mode. Now I'm actually only exchanging 1 process data word in each direction, but it's okay to set this to 3 PD. It'll be just fine. And then finally I clear my 3 POs just by setting them to 0, so I give them an initial value. I set up my second record variable, Fieldbus2. This is the one associated with the PIs that I'll be sending back to the PLC. I set the length to 3, again to select 3 PD mode, which is fine even though we're in 1 PD mode. And I clear my 3 PI variables so they just have zeros in them at this point. Of course, once we start talking to the PLC, these will go outwards and the POs will come inwards and they'll have values. Last thing I did is I set my ramp value to a fixed value of 1 second in each direction by setting ramp 1 and ramp 2 to 1000 milliseconds, calling setsys with the IPOSplus ramp constant and passing in the first variable. I only have to do this once because it's never going to change. So we're now good to go. We move into our infinite while loop. And we're not going to look at all this code yet. We're just going to look at the first part of it. Remember, DI10 is our enable signal. That indicates whether the VFD should be listening to the Fieldbus or ignoring it. If DI10 is on, we listen to the Fieldbus and we follow the commands that come through it. If it's off, then we ignore the Fieldbus, and if we were running, then we need to stop first of all. Let's look at just the first part of it, and we'll come to the else statement later on. If DI10 is on, that means listen to the Fieldbus. So we call the function setTask, and we turn on task number 3, the background task, which is going to watch the Fieldbus, and we assign it to the function task 3. So what we're doing is we're starting up multitasking and letting task 3 begin to run, and when it's running, it will take care of most of the Fieldbus activity for us. Now, we'll come back to the else part later. I want to just jump forward and look at task 3, because this is where most of the action happens. All right, so task 3, once it's started up, is going to do a number of things. The very first thing it does, it's going to retrieve the POs from the Fieldbus, or rather the single PO, PO1. It calls the function getSys, it passes it the record variable Fieldbus1, and it uses the constant GSPO data. So that tells it to go out and get process output words from the Fieldbus. So it's going to call that and put it in the record variable. Now, once it's done that, the record variable will contain PO1, it will be populated, and then I need to harvest the information I care about from that word. So what I do is I extract the mode bits. Those are the 3 bottom bits that indicate whether I should run or not run. I do this just by bitwise ANDing it with hexadecimal 0007. That masks off all but the bottom 3 bits. So mode will now contain a number, and if that number is 6, I'm allowed to run, and if it's anything else, I'm not allowed to run. We extract the setpoint bits, that's 3 other bits a little further up in the word. We do it by, again, bitwise ANDing with hexadecimal 0E00 and doing a shift of 9 to the right. That will take our 3 setpoint bits and put them in there, so we'll have a number from 0 to 7. And then lastly, I extract the direction bit by bitwise ANDing with hexadecimal 1000, shifting to the right 12 times. That will extract my direction bit. And I'm going to use those 3 pieces of information to decide how the drive will run or not run. So to decide if it runs, I'm going to simply check mode and see if it equals run, which is a constant I've already created. It's equal to the number 6. So if mode is 6, it means I'm allowed to run. If mode is not 6, I'm not allowed to run. So the if statement decides which one we're going to do. Let's assume we're going to run first. The first thing we have to do is set our speed. Now, I could have put code right here to pick the correct speed, but instead I farmed that out to a separate function called setSpeed, which I wrote. It's actually right above task 3. We'll look at it in a minute. But this sets up the speed. It programs the correct set point based on whichever value came in on the set point bits. So we can just trust that's been taken care of at this point. Next, we have to determine what direction to rotate. So we look at the direction bit, and if it's clockwise, we chase our tail in the clockwise direction, and if it isn't clockwise, we chase our tail in the counterclockwise direction. This is the standard technique we've been using for jogging. We take the current motor position and we add or subtract 1 rotation, 4096 increments from it, and we put that back into target pos, and since the drive is enabled, it will immediately start running and chasing its tail. So we get it rolling. And then the last thing we do is we're going to send some feedback to the PLC telling it that we're running. So I set PI1 in record variable Fieldbus 2 to the constant running, which is a 1. It puts a 1 in the least significant bit position. Now, we haven't actually transmitted this to the Fieldbus yet. We've just put it in the record variable. We will transmit it in just a second, but we've updated status. Then we're finished with our part of the if statement. Of course, we skip the else, but we go down here, and this is where we report back to PLC. We call the setSys function. We use the constant SSPI data, and we give it the record variable Fieldbus 2, and that will take that single PI that we've just updated and send it back to the PLC. And since this is a background task, it just executes over and over and over. So it's just going to continuously retrieve PO1 from the Fieldbus, assess it, do what it says to do, and send status back. And it's just going to happen constantly in the background. So this is where multitasking really shines. It's doing a task that has to just run endlessly, but it kind of separates it from the logic of the main program, so the main program can do other things. So it's actually pretty elegant. This is where multitasking is really just perfect. All right, before we finish up task 3, we have to look at what happens if the mode is not run. In other words, we need to stop. That's what the else handles. The else does this. If it's not run, therefore it is stop, do a rapid stop by calling access stop with the constant ASRStop. So that will bring things to a screeching halt. And remember, when you call a rapid stop, you have to re-enable the access if you ever want to run again. So we call access stop with ASEnable to just re-enable it. And then we set Fieldbus 2, which is our record variable. We set PI1 in that to the stopped value. We're going to tell the PLC we just came to a stop. And then, of course, when the if statement is over, it will transmit it back to the Fieldbus. So we've covered our bases pretty neatly here. This handles all those possibilities quite well. Now let's go back and take a look at that set speed function that I wrote. Okay, this is another user-created function. I just did this to make my code more readable by dedicating this to its own function. It's really just a giant switch statement. All it does is it looks at the set point bits, which will be a number from 0 to 7. So we have 8 cases here. And what it does is if it's 0, set the current speed to the constant set point 0. If it's 1, set it to set point 1, and so forth. So this is just determining which set point to use, grabbing the right constant. Then it sets current speed 2 to current speed 1, because remember, we have to set speeds for both directions, so we have to set up 2 variables that are contiguous in memory. And the final thing we do is we call the setSys function with the constant ss_posspeed, and we pass it current speed 1. It will find current speed 2, and it will set the motor speed. So this function just whizzes through and does this really quickly, and that is it. Final thing to look at, we need to go back to main and look at the code that we didn't cover before. What happens if we turn off DI10 to tell it to start ignoring the Fieldbus? Well, what it does, it jumps into the else code here, and it does the following things. First of all, it shuts down the background task, so we stop listening to the Fieldbus. It calls setTask, it feeds it st3 stop, and essentially disconnects that function. It then calls rapid stop from access stop, so it brings the access to a screeching halt if it happens to be running. It then re-enables it so we can run in the future. And then the very last thing it does before it goes silent is it sends stopped back with PI1 to the PLC just to confirm to it, yes, I did stop because we flipped that switch off. So it sets the PI1 variable within the record variable Fieldbus 2 to stopped. It calls setSys, passes that. One more PI goes back to the PLC, and then it's kind of radio silence until we turn DI10 back on. That is our whole program. Not too big, not too complicated, takes real advantage of multitasking. You can see Fieldbus communications isn't that hard. So let's just compile it and make sure it's error-free. And it is. And now we're ready to run it and give it a test with the Ethernet Master Simulator. So I will run it, and then we're going to fire up the Ethernet Master Simulator, plug a cable in, and see if our drive operates. All right, well, time for a test. As you can see, I've got the Ethernet Master Simulator running here, and I haven't connected yet, but I will in a second. But I want to tell you a few things about it before we go any further. The Ethernet Master Simulator is just a test tool, therefore it is a little bit cantankerous. It can be troublesome at times. Occasionally it'll just quit or do other obnoxious things. Just be aware of that. SEW offers it for free purely to help you with development, so it's not really a very robust product. So be aware it may bomb out while you're playing with it. I should also mention sometimes if it quits, it will cause your MoviDrive B to generate an error that's basically a Fieldbus timeout error, and the only way you can really clear that is to power cycle the VFD. So if that happens, don't drive yourself crazy trying to clear it in the usual way that you clear faults. Just power cycle it and everything should be fine. All right, now we have to test all the possibilities that can happen here. We have to test run and stop. We have to test all the set points and all the directions. And if you were doing this for a real application, you would test every single one. I'm not going to put you through that. I'm going to just run a few examples. But I am popping up a little chart right here to show you the hexadecimal numbers that you must feed to the Ethernet Master Simulator in order to exercise every single function of the drive. So we're just going to do a few of these. Okay? So that said, let's dive in and go. You can see my program is running, but I'm not connected yet. I do have a cable connected from my PC to my Fieldbus card, and I've fired up the Ethernet Master Simulator. Now the first thing I need to do is switch to Modbus TCP mode because that's the mode I want to use. I also need to set RPI to 500 milliseconds, and then I click Open Session. Okay, my session's opened up. I'm going to now start it. Okay, now the first thing I'm going to do is turn auto update off. And I'm going to just type in a 6 and see if my drive starts running. That should run with set point 0. And I click update PO and nothing happens. But I just remembered something. I need to turn DI10 on. If you look up there at the top of the screen, you can see that task number 3 is not running, and therefore the Fieldbus is being ignored. So let me take care of that by flipping DI10 on. And hooray, the drive is spinning. All right. Let's reverse direction. I'm going to put 1006 in. And it's spinning the other way. Let's go back. Now let's try a stop. We'll put a 0 in here. And it stops. Let's try our fastest speed. I will put in E6. And I'll go the other way. Works great. Let's bring it to a stop. And finally, let's do one last thing. Let's put in a 6 again. And let's confirm that our PI coming back is correct. The drive is running. Notice we have a 1 in PI1. Let's stop it. Put a 0 here. Goes to 0. Start it up again. And one last thing, I'm going to turn DI10 off. And the drive should stop and we should get a 0 in PI1. Let's confirm that. And we got it. So, I think everything is working pretty well. That's it. Okay, well, the time has come to give you a big congratulations. That's it for the motion control part of this class. You've gotten through the bedrock. We've now looked at motion control and all the different things you can do with a MoviDrive B under IPOS control, and we have finished. So, really splendid job. Good job hanging in with all 14 of these sessions and all those programs you wrote. You have done a tremendous task. Just a reminder, I mentioned this at the beginning of the class. I'm going to mention it now at the end. If you have any questions about this class, anything in it you didn't understand that really just frustrates you, feel free to contact the training department at SEW Eurodrive. The email's right here, training@seweurodrive.com. And please include the words IPOSclass in the subject line of the email just so it gets routed to the right person. We will be happy to do what we can to answer your questions if you really get in a jam. Now, one little caveat to that. The training department cannot provide assistance for your application needs. In other words, if you're writing a program for a project you're dealing with and you get stuck, we are not a technical support line. We can't help you with general IPOS questions. We can only help you with questions connected with this course. So if you have an IPOS question for a real application, please contact your local SEW Eurodrive Regional Engineering Group for help, and they can route you to an appropriate person that can assist you with that. So that brings us to the end of session 14 and also the end of our class. Congratulations for hanging in there. I hope you learned something and that you're now excited to dive in and start writing some IPOS applications and really taking your VFD and control systems capabilities up to the next level. So, gold star, really good job. Congratulations, and I'll see you in other classes. Bye-bye.